we are live. This is Math 75, analysis for business and economics, or something like that. Section 1.2, we're talking about functions. We're going to have a big old function party. It's going to be awesome. So let's dive right in with some definitions. Everyone loves definitions. We're going to start off with an independent variable. There are a lot of definitions for this. They tend not to be very helpful. So let me give this a try. Hopefully this will make some sense. The independent variable is the variable you begin with, or the input. This will usually be x. It's independent because it's the one you choose to begin with. Then the dependent variable is the variable that depends on the independent variable. It's the output. For our class, this will frequently or usually be y. It's called dependent because we plug in x and find what y is. We can't just choose a y usually. Then, and here's the exciting part about this section, a function. Now, I am assuming that if you're taking this class, you have studied functions in a previous class. If you have forgotten them, or if you've never studied functions, what we're talking about here will not be enough. So you'll want to talk to me, talk to the tutors, go online, get some information about functions, really study up, because this is going to be a big part of this class. Okay, a function is a relation. A relation is basically a connection. It could be, you could even say a relationship. It is a way of relating two sets together. It's a relation between two sets so that each input, which is mostly going to be an x, corresponds to exactly one output. So I've got some examples to try to imagine what the heck we're talking about here. So the correspondence between a person and their birthday is a function. In that, most people have a single official birthday. Now, it is possible that some people celebrate a different day, but if I ask you, what is the day you were born on, unless you were born like over like the minute that spans midnight, most people would have a particular day that they were officially born on. So this is a function. Each person can be associated with their official birthday. The correspondence between a person and their eye color. And here people usually say, oh, easy peasy, it's a function. And the answer is, it's not a function. At which point, a lot of people are like, what? But what happens here is there are some people who are born with two different colored eyes. So one person might have one blue eye and one gray eye, or one blue eye and one green eye. And so if you associate a person with an eye color, it's not a function, because some people, this arrow goes into two different eye colors. So one person corresponding to two different eye colors, not a function. The correspondence between a person and their pet. And you have to think about this. Now, some people don't have pets, so that's tricksy. But then some people have a lot of pets. So if you have a person corresponding with a pet, somebody might have more than one pet, in which case this is not a function. More than one eye color, more than one pet, only one birthday. So the goal of a function is that a function is going to look like this. This is not a function. And I'm going to introduce you to a shorthand So mathematicians are used to single letters. We don't use a lot of the alphabet all at once. And so a lot of times mathematicians get tired of whole words because there's a lot going on inside which you really don't need. I start the word, I end the word. You know what the word is. Why bother with all the other letters in the middle? It's just taking up extra space and time. So F followed by an N underlined up high. It's an old-fashioned way of doing a shorthand, but that represents function. You'll see me write that a lot because my teachers wrote it a lot. Okay, so a function means each person over here corresponds to one element over here. If one person or one element here corresponds to more than one element, then this is not a function. Okay, vertical line test. A way to visually determine whether a graph represents a function or not. And it usually involves a ruler. Yay, I got a ruler for this. And I got a ruler you can see through. Ooh, isn't that fancy? Ooh, look at that. Okay, so basically the idea is this. I have drawn a very awkward graph using Microsoft Word. And the question is this the graph of a function or not? And for this, I think I'm going to use a, let's see, I'll use blue. Let's see if that shows up. So if I take this, if this is my vertical line, there we go. Vertical is the one that goes up and down, not side to side. If I take my ruler and I push it, I slide it along the graph, I can see, for example, at this value of X, I've got that Y value right there. So a single value. At this value of X right here, I've got this value of Y, right? So this value of Y corresponds to that X. This value of Y corresponds to that X. Everything is fine. Now let's look what happens right here. Right here, if I look at this vertical line, trying to do a dotted line along it. So at this vertical line right there, how many times do I cross through the graph? There, there, there. So right here, we've got one X value corresponds to 3 different Y values. So this is not a function. Now, what would a function look like? Well, if I were to very carefully take a little card, which I am grabbing right now, if I were to take a card and I were to cover up this part of the graph so that the graph were only just right here, this would pass the vertical line test because at any vertical line, it only crosses the graph once. This part, however, is just a mess. This one goes through 3 points. Over here, it goes through 3 points. Here, right here, it goes through 2 points. So that's where it fails. It fails the vertical line test here. And so that means the entire graph fails. If you only fail in one spot, you still completely fail. It's a really, well, you know math. It's a hard test to pass. So what would a graph of a function look like? That's a good question. Am I going to get to one of those over here? I'm thinking not, because we're going to go right into something else. So let me go ahead and do some sketches. Now these will be sorry, these will be terrible graphs, guaranteed, because I'm freehanding them and just sketching them. But an example of a function, would be something like this. If I drew a straight line, this line right here, that is a function. If we look at the vertical line test, if we take a look at a ruler, it goes through once, Every x value corresponds to a single y value. That's a function. Okay, what else would be a function? Well, we haven't gotten to them yet, but parabolas, a lot of parabolas are functions. They're fancy, they curve, they smile, they help us talk about things like profit and revenue in sort of reasonable ways. Let's take a look. As I move along here, I only cross the graph once. So a parabola, also a function. Let's talk about things that are not functions. Well, I said a lot of parabolas, ooh, that's a little wiggly. We're getting wiggly, getting jiggy with it here. A lot of parabolas are functions, but this one is not. And the reason for that is I've turned it sideways. Now, if I look right here at this point, see how the ruler hits twice here and there? This is not a function. If a vertical line going through the graph intersects twice or more, it's not a function. What else is not a function? Well, I've kind of run out of room, so I need to get a really skinny function. How about a cute, oh my gosh, isn't that adorable? Look at that adorable little circle. Oh my goodness. What an adorable little circle. However, it is hiding an evil truth. The evil truth is no matter how adorable it is, look at that, not a function. A vertical line goes through at two spots, okay? So anything that kind of folds in this direction, not a function. Okay, woohoo. So we got functions and not functions. Let's go on to how to write them. Oh, don't look at that yet. Oh no, don't worry about that. Oh, don't worry about that either. I'm having trouble. There we go. See, to be a math professor, you've got to have all the mad skills. There we go. So function notation. And I got to tell you, very few people love this. It's okay if you do not like this. However, we are going to be using this. This is going to become the way we write down everything we're going to do in this class from here on out. And so it is important that you become familiar with it, even if you don't like it. You can hate it the whole time. My job is not to teach you to love math. My job is to teach you how to use math. So that's what we're going to do. So again, this is not an introduction to function notation, although I have given you the name. So you can go ahead and Google this to your heart's delight. So what I'm going to do is I'm going to assume you're at least familiar with the idea. Basically, I've got the name of the function, name of the function, and then in parentheses, I put in the independent variable. And I pronounce it f of x. So this is called f of x. And basically what I'm going to do is I can give, for example, right here, I'm going to write it a little bit bigger. F of x, I can give a rule, is equal to 2x cubed minus 3x squared plus 1. And then g of x equals 3x. So I can now name my functions instead of calling them both y. Now one is f and one is g. Why do we use f so much? Well, f stands for function in many languages. It's just pronounced in slightly different ways depending on the, so a lot of the Romance languages, it's function or something similar. It certainly starts with f. So, and I believe in Latin it's something similar too. So what do we do? Well, if I know that f of x is, and again, I'm going to write it again, 2x cubed minus 3x squared plus 1, and I want to know what f of 3 is, what I do is I take the 3 and put it wherever the x was. So 2 times 3 cubed minus 3 times 3 squared plus 1. Here, I'm going to try to use my handy dandy highlighter. Hopefully not take us to Smeary Town. So wherever the x was, I'm going to put in the 3. It's a little Smeary Town, but hopefully not too terrible. So 3 cubed is 27. So I've got 2 times 27 minus 3 times 3 squared is 9 plus 1. So that's 54 minus 27 plus 1. 54 minus 27 is 27. Plus 1 is 28. Okay. So then let's try f of 0. F of 0 means wherever I see the x, I'm going to put in a 0 now. So this will be 2 times 0 cubed minus 3 times 0 squared plus 1. And again, hopefully I will not take us too badly to Smeary Town. There we go. And this one's a lot easier because 0 cubed is 0. So 2 times 0 minus 3 times 0 plus 1, that'll just give us 1. Okay. Now how about f of t? Well, f of t is going to be what happens when I take f of x and I plug in t wherever I got the x. So 2 times t cubed minus 3 times t squared plus 1. Look at me learning to do the yellow first and then write in the t. I'm learning. And what this means is if I had f of x, this is now f of t. I'm just rewriting the whole thing in terms of t. Okay. Next up, this calls for g of 12. Now I go to g, so I have to find the g. G of x is 3 times x. G of 12 is 3 times 12. G of x is 3x. Use a slightly different color here. G of, because this is g. There we go. G of x equals 3 times x. G of 12 equals 3 times 12, which is 36. And now I want g of, now this one's a little weirder. Perhaps a lot weirder depending on your perspective, because inside here I want g of x plus h. So whatever's inside, g of x equals 3 times x, g of x plus h equals 3 times, and again, I'm getting smart and I'm doing the color first, 3 times x plus h, which then I know how to do that. It's just 3x plus 3h. And I'm looking at this and I'm staring into a computer and I have no idea how you feel about this, but I get the feeling it still doesn't make sense. So I'm going to grab another piece of paper and I'm going to go ahead and do some more. If f of x equals 2x cubed minus 3x squared plus 1, which f of x could mean a lot of things. So let's do f of 1. That's going to be 2 times 1 cubed minus 3 times 1 squared plus 1. So everywhere there was an x, I'm putting a 1. So that 1 cubed, 1 squared. So this is 2 times 1 minus 3 times 1 plus 1 is 2 minus 3 plus 1. 2 minus 3 is -1 plus 1 is 0. Okay, let's do f of, what did we do before? We did f of 3. Let's do f of 2. 2 times the quantity 2 cubed minus 3 times 2 squared plus 1. Everywhere there was an x, I'm now putting a 2. So 2x cubed becomes 2 times 2 cubed. Minus 3x squared becomes minus 3 times 2 squared plus 1. 2 times 8 minus 3 times 4 plus 1. 16 minus 12 plus 1 equals, you got it, equals 5. And what if I did f of x plus 1? Oops, I can't do that in this one, can I? Nope. Okay, let's, I realized as I'm coming up with things that you guys can do, I am not prepared to teach you as much as you need to know to do that one. So right now we're gonna, oh, wow, this is, wow, we had a bad day. Okay, so let's see, what could I do? How about f of r? Let me do f of r. So f of x was 2x cubed, f of r is 2r cubed, minus 3x squared minus 3r squared plus 1. How about f of 10? 2 times 10 cubed minus 3 times 10 squared plus 1. 2 times 10 cubed is 1,000. 10 squared is 100. So it's 2,000 minus 300 plus 1 is 1,701. And again, what I want to say is function notation is not easy. So if you've never seen it before or you truly do not remember it, you want to come talk to me. You want to talk to the tutors. You want to go online and Google it and let us all together, it takes, what did they say? It takes a village to teach someone function notation. I believe that's the saying. So, talk to everybody and we can give you tons of practice so that you can just practice this up before you go on. But that's the first part of 1.2. Next video, we'll continue on with functions. Woohoo, math on.